Welcome back, guys. Our next speaker will be talking about a WebAssembly VM in Nock. Please welcome Kirill Afonin. Sorry, I butchered your name.
Thank you.
Take it away.
Okay, well, hello everyone. It's great to be here. As the presenter said, I'm going to present the WebAssembly virtual machine in Nock. Curtis did a great job explaining the current state of the software stack that exists on top of Nock. So I will not dwell too much on this slide. I will just say that even though this Nock ISA is this tiny, tiny thing, we have a totally real software stack that exists on top of it that comprises the self-hosted language and operating system or operating function, if you like it more like that. That includes the file system, the networking protocol, and software distribution, and so on. And an interesting challenge was, well, since we only have Nock, since the Nock machine can only run other Nock code, well, how do you run conventional software in this environment? Say you have some piece of code written in C, in Rust, in JavaScript, Python, whatever, and you would like to run this on Urbit. Now here I would like to make kind of a separation between running code on Urbit versus running code alongside Urbit, or like with Urbit. Because you could definitely set up a runtime that runs in a separate process, and then you could set up something like an IPC communication between your Urbit and that process. But the issue with that is this software would not be able to be distributed through the Urbit network itself, because in addition to a setup that would be necessary in your Urbit environment, which would be basically automatic and close to none, in addition, you would have to set up this process that would run in parallel. So the challenge here is to actually run regular software using Nock interpreter itself. And, well, there were kind of different ideas. Back in the 2010 blog post by Curtis, he mentioned making, for example, a C interpreter in Nock and like jetting that. And others had ideas of porting a JVM on Nock. But the solution that we have right now is the WebAssembly interpreter in Nock. WebAssembly has relatively small specification size, so it was somewhat easy to implement. That was done in early 2024. And it was impractically slow, which was to be expected, actually. It is expected, and at this point I would like to make a little digression on how we optimize running Nock. And the first optimization that we do is jetting code. So as Curtis mentioned in his speech, the decrement is O(n) since you need to count up from 0 to the n-1. Similarly, the best case for multiplication of the atoms is something like O(n) squared. Floating point arithmetic, according to my estimates, is something like n cubed. And in all of these examples, n is the value of the atom, of the integer. If you want to think about this in terms of like a bit width of the atom, you need to add a little exponent in here. So it's e to the n squared, e to the n cubed. So obviously, like, no normal mathematical operations can run in this environment well. And this is where we use the jet system, which recognizes the standard lib functions that we have defined in Nock and runs an optimized function instead. So first I will give just a tiny primer on Nock itself. Everything in Nock, and so everything on Urbit, is a noun. And a noun is either an atom, which is a natural number, or a cell, which is an ordered pair of nouns. So since a cell is a pair of nouns, and a noun can be a cell, you can have cells within cells within cells. So you can have arbitrary data structure as this basically binary tree whose leaves are atoms. And so 42, that's a noun. A pair of 0 and 1, that's also that's a noun. And pair of pairs of zeros is a noun, and so on. And in this, so okay, we have nouns now. And what does it mean to run Nock? Well, to run Nock means to run a Nock function, which is this small function defined in T-shirt, with two arguments, a subject and the formula. Where the formula is code, that's basically a sequence of Nock instructions encoded into a noun. And the subject is a essentially an environment or scope within which Nock is running. And the product is obviously also a noun. And, well, that was the way we run code, but how do we store code? How do we handle it? And we store it in these pairs of, again, like code and data. Here it has different names because we use them slightly differently. And for example, when you have this pair of code and data, or battery payload, in order to run code, you use the entire core as the subject, and the battery, or sometimes only a piece of that battery, as the formula. For example, that enables recursion, because the battery can now refer to itself. Payload here would include something like arguments, global parameters, or imported libraries, which would also be cores. And callable functions are represented in a similar way, except we split payload into another cell, and the sample here is the actual argument. And the calling convention for these callable functions is replace the sample and run the code. And whenever a core is called in our Nock interpreter, its structure is checked against registration information for each jet. And when we check for every registration entry in this table, we check the battery for the exact equality, and we check the payload against the template that we have saved in this table. And the template is either a constant noun, or it's a core, a registered core, and another registered core at some known position. And so that again, you can see that the template is this recursive structure. Like you can have a registered core, which inside of it has another registered core, and so on until like the deepest core will have just a constant. So like the first, like on the bottom of the slide, there are 3 examples. The first core is kind of the root of our registration sequence in the standard library. Its battery is just 0.3, and the template for its payload is just 138. So we're just checking basically the entire thing for equality, and if it checks, then that means that we matched with that core. The second example is the first layer of the standard library. For that one, the battery is much bigger. It contains 33 functions, so I'm just using a shorthand here. And the template for that one is to have a core K138 at the tail. So +3 means basically at the tail of the core. So again, in this example, it's again just an equality check. And the last example is an actual callable function, which is add, so like to add 2 atoms. And here we will check the battery, and we will check, according to the template, the tail of the core. So we check the battery here, we check this highlighted part here, but what we don't check, what the template essentially masks out, is this part here, and this is basically where the arguments are. And if you remember, the calling convention is swap out the sample and run the code. Essentially, no matter what kind of argument you have there, the jet registration match will occur, and instead of running naive Nock and like having to increment your atoms until you actually get the sum, instead you will actually run an optimized function, which will just add 2 atoms together. So now we are actually back to making a Wasm interpreter, and so now we understand what the next step was supposed to be, and that is to jet the Wasm interpreter, to make a jet. And a naive approach would be to make something like a function which just handles function calls to Wasm. So say, for example, you represent the state of the WebAssembly virtual machine as some kind of noun state, and then you make a function which takes a name of a WebAssembly function as just a string, a list of arguments, and the initial state, and the product of that function would be the result of the function call and the updated state. Now that actually, well, it would work, but it would be quite slow, because first of all, we are kind of in this immutable environment where we cannot update nouns in place. And on top of that, since Jet would probably use some kind of optimized representation of the WebAssembly virtual machine state, like it's not going to represent it as just nouns, it's going, we will probably want to use, like, I don't know, some C structs, some arrays or something. We would basically have to take the noun, we would have to marshal it into this optimized state representation, run Wasm, and then marshal it back into a noun in order to produce it, which is just prohibitively slow. And the approach that I decided to taken instead is to basically batch the Wasm interactions into a single script, which is basically a state monad, and then make an interpreter function which takes a Wasm binary, so just Wasm code, which takes that script and that runs that script against the binary. So we instantiate the state, we run the script, we modify the state, we produce the result, we discard the state, we don't actually produce it here, so we don't have to marshal it, we just produce the result. And that interpreter function, when we write it in Nock, well, we actually write it in Hun and compile it to Nock, for its Wasm backend, it will just use the Wasm interpreter that was built previously, but in the jet, it will use much better interpreter, much faster interpreter, which in our case is a Wasm 3 fork, which we additionally hardened for determinism. So remember that Nock is like precisely deterministic. And here, for example, I had to make floating point operations deterministic by using soft load. Had to like harden parsing and memory allocation. Okay, so once we have that, once I had this kind of design idea, I needed to define, well, how are we going to handle scripts? How are we going to represent them? And the first idea was to basically have a head-tag union where, so like every piece of the script is going to be a cell where the head of the cell is just a number from 0 to 4, which like encodes an operation that we're going to perform. And the first 3 operations are like basic WebAssembly operations, like we call a function with like the name of the function and the argument list. Or we perform a read from the WebAssembly memory, or maybe we write something into the WebAssembly memory. And like just 3 simple operations. And the last 2 are, well, what makes this monad actually a monad, so like a bind and pure. So bind, well, just like every monadic bind, it contains a monad to run, and then a continuation, which is basically a function from a list of values to a new monad, and pure is just, well, return this result, which worked. And it worked just fine, but the issue was that the product of such script was type monomorphic. It would always be a list of basically interpreter values. Which, for example, in the best case scenario, that meant that whenever you called something, some kind of script, you would have to assert the type of the script. Like you have to assert that, okay, like the list has exactly one entry, and that entry is like exactly I32 atom, and then we take this atom and we do something with it. Or like in worst case scenario, let's say, for example, you want to read like a JSON object from WebAssembly memory. Well, now you have to basically separate this into 2 different things. You need to first load the JSON object into Nock as this list of values, and then you need to like parse this list of values in order to produce like a JSON noun, which basically means the main script is twice as big as it needs to be. The number of functions in your like Wasm supporting library twice as big. So it's just like excessive boilerplate, and it wasn't really nice to use. And so then I kind of asked myself, well, is there a way to, alongside with like actual immediate arguments of each of these operations, is there a way to kind of record their type, the type of the result? And it is, of course, possible if you define the building blocks as like actual functions. So if you define them as functions that take like this interpreter state and produce a pair of result in the new state, well, then yes, of course, you have like function signatures at compile time, and then you could use polymorphic bind in order to actually like produce a polymorphic script. And the way it would work in a script interpreter in Nock was fairly straightforward. You just instantiate the state as a noun and pass it to this function, and you just get the new state and the result, just return the result. But how would that work in the jet? Well, the jet would, and this is like kind of interesting, I think the way I made it is that we switch over different batteries that we have. So the batteries, this is the code that we have in this like function object. And we switch over this code as if it was just like head tag. And we switch over it until we get a match. And if we get a match, we check that the payload, that's the data part of this function object, we check that it's well formed and that we have arguments inside of it, and we extract them and use them in order to operate with Wasm 3 state. Well, that's basically like having a jet system within the jet, right. And the way And so, for example, the way it worked for the legibility of scripts is that now you could have a simple function which does both the loading or storing of data into or from Wasm memory, and also does like all the encoding and produces a type value, which was quite great. And this works for this greatly works for one-off tasks. So whenever you have just some simple, not simple, it can be quite big, but if you just have one script to run against the WebAssembly binary, it works just fine. So for example, numerical algorithms, compression cryptography, at some point when I was developing this interpreter suite, I had to also support the text format of WebAssembly, which is WAT. And instead of writing my own parser, what I did is that I took the WAT to Wasm transformer written in Rust, I compiled that to Wasm, and I ran it using the Wasm interpreter itself. So that was kind of the very first example of using some code written in Rust within Urbit. It worked just great. But since we drop the state when we return from this function, that means that we cannot really have I/O. For example, this Wasm VM cannot really meaningfully interact with the outer world, because every jet computation, that's the pure computation, which means that it happens within one event of our server. But I/O, it spans multiple events. We release something into the world, and then we hear back, and we want to continue doing something. And again, this could be fixed by adding a state return here, but that means that we would again have to serialize it from this optimized representation to nouns and back. And I didn't want to do this. Now, I found a trick around it, and if we think what we do instead of explicitly returning the state of the Wasm virtual machine as a noun, we use the event log of interactions with this virtual machine as the formal representation of that state. And then we go ahead and make a function which takes a Wasm event and an old event log, and what it does is that it basically appends a new event to that event log and runs the whole event log, producing the result. Now, obviously, that means if you're running this naively in Nock, or if you are not using any tricks, that means that for every new addition of an event to that event log, you have to rerun the whole thing, so this whole thing scales quadratically. But what the jet does is that it understands that the state of the WebAssembly virtual machine, even though it is not a noun, it is still a pure function of the event log. So what we can do, we can kind of pack it into this fake noun and put it into a lookup table using the event log as a key. And so later, when we call this jet with a new event log, we can look up a value in that lookup table and basically continue. And that brings me to a second digression on Nock optimization, which is memorization. And there are basically two axes. Memorization can be either transient or persistent. So transient means that it only works here and now. It will not persist into future events of the Urbit server. And persistent means that we can actually save it for longer. Complete means that let's just start with this example. For example, complete and transient memorization. What is this? Well, it just means that for current computation of Nock, of subject in the formula, we use the subject in the formula as a key, and we save the product as a value, so that later we can look it up. And that's just available in user space. There are no restrictions on using it. The second example is the complete persistent memorization, which means that we will actually save this value for later, so that in future events that our server will handle, we could also use this. Now, this is not available in user space for some reasons, which I would like to not go too deep into them, but it is available to the kernel space. So for example, right now we cache reads from the kernel space by the user space, but soon, for example, the entire build system would be cached that way instead of using explicit caches. Network packet serialization, deserialization would also be memoized in that way. Bootstrap sequence itself, so having basically, the bootstrap sequence is essentially you take the already compiled Hun compiler, you compile the new version of Hun compiler and so on. So you actually build this operating function that could also be memoized. The transient partial memoization, this is a trick that compiler jets do. So for example, what they do is that they basically do the same thing as here, except they mask out some parts of the subject that don't actually affect the result. And that allows to speed up the compilation greatly. And finally, the persistent partial memoization is what I ended up using. So I save the WebAssembly state into this noun. So basically, I take the jet state, I make it portable by, for example, walking pointers and turn them to offsets, and so on. It gets packed into this basically huge noun, and it gets saved into the table. And to kind of show you how it looks like, here is an example of, well, here's just some Wasm. And essentially what this Wasm does is that it calls an acronym function like 10 times, which just takes something like a half second to run it with arguments like 3, 9. And then in between it, it performs an external call for some information which is not available to the Wasm interpreter itself, or like to the script interpreter even. And if you don't use memoization, the way it ends up working is as you kind of go further and further, like resolving these external requests, it'll take longer and longer to run Wasm because it will essentially have to replay the entire event log. So here, it started with 400 milliseconds, now it's like 8, and so it's 400 milliseconds more every time. So I might as well just interrupt it. And if I turn on the memoization here, just put this, commit it, and then we run it, well then actually every time we perform an external call, the state is going to be saved into the persistent cache. And that allows us to run the whole computation much faster, of course. Now, to wrap up, what have we achieved so far? So we have a working jetted stateful Wasm interpreter in Nock with minimal overhead. Well, minimal overhead that definitely applies to the stateless version. There is some overhead that could be eliminated in the stateful version, which we might discuss if you'd like to. And as for the actual things built with it, so for example, Urbit Messenger, which is clone messenger, it has a possibility of adding functions which handle events in group chats. So for example, somebody posts a message or replies or reacts. That's an event that could be handled by a function. Previously, this function would have to be written in Urbit language, in Hoon. But what I did is I made a JavaScript integration so that this entire thing could be entirely written in JavaScript. And what happens is that this JavaScript gets kind of turned into this Hoon function, which is then later applied. As for the next steps in this direction, I'm working on a software development kit for running IO scripts on Urbit. So for example, if somebody wants to write a JavaScript script that maybe fetches some data, does some compute on it, saves it in the file system so that they can later read it, that would be possible without writing a single line of code. And another direction that could be taken is user space agents, so it's actually stateful apps. There is a little bit of kind of concern here because, as I mentioned before, we represent the Wasm state as an event log, which means that it only grows, it never shrinks. And so you want to add, if you want to have a persistent agent, you want to add some kind of capability of that agent to commit its state into a noun to truncate the event log. So that's it for now. Thank you for your attention. Any questions, I'll be happy to answer them.
Any questions?
So what is the overhead total comparing to running Wasm in natively?
Well, running Wasm natively, you mean in the browser?
Yeah, any Wasm executor can.
Oh, yeah. Well, because I would, for example, separate the overhead of running Wasm in Wasm 3 interpreter versus running running it in the browser. The browser is just faster, that's the fact. But for stateless or Wasm, the overhead is essentially, well, we still have to run Nock in the scripts, because remember that scripts are basically, like even in this example, you have this function. So like you need to actually compute the continuation on it, and that's not. So like there is, of course, like some overhead, but it's kind of like irreducible. Like it just has to exist. As for this stateful Wasm, for like the things that could already that could in theory be worked on, there's probably feedback from the microphone. So like for stateful Wasm, I would like distinguish two kinds of overhead. One overhead is like actually saving the, it's like having to traverse the structs and making them portable and then saving them into the persistent data structure. That, from like a little investigation that I did, that's like on the order of milliseconds, which is like fine if you're doing I/O, because I/O is like way slower than that. Another thing is that, so for example, even in this like small Ackermann example, if you notice that in stateless versions, so if we didn't save any state, it took like 400 milliseconds to run. Whereas in stateful version, it was 500 milliseconds. That's slower. But why is it slower? Well, it's slower because kind of the data non-locality. We have Wasm stack, so that's the stack that Wasm 3 actually uses. And I have a separate stack for handling computation suspension, essentially. And these are located in different parts of the memory. And so like if you are accessing them both, you are going to miss a one cache. And that's like a strong hit on the performance. However, it only happens if you are handling control flow operations, which in this case is basically function call and the loop. Now, Ackermann function is like only functions, like 100% of the runtime is like function calls, which is like not very representative of like regular things that we are doing with WebAssembly, but like still, it could be optimized. Like I could, in theory, probably make it so the stack is used both for Wasm 3 execution and the suspension. It's just, I couldn't really figure it out, but maybe I'll figure it out in the future. So yeah, like 2-3 milliseconds for saving the state and something like 20% speed reduction when running in stateful Wasm, but that could probably be reduced.
Thank you.
Anyone else? Well, great talk. Yeah, thank you very much.